methods available in MATLAB also is the pole placement based method for the control design, right? So we'll just begin with this. So what we have learned from our earlier classes has been this thing that, well, if you have a system with its dynamics available to you in the form of a state space matrix, then if I can figure out whether the eigenvalues are all inside this specified area, then we will call it a stable system, right? In some other specific area, then it's unstable, and there is also this clause for marginal stability and all that. And similarly, if we look at the S domain based transfer function for the system, we will look for the position of the poles, and if they are all in the left of plane, then again it's a stable system. Otherwise, on the imaginary axis, it's marginally stable, and if it's any pole on the right of plane, then it's an unstable system, right? So we'll make a few assumptions here. First of all, we are trying the simplest kind of design. So we are assuming that all the state variables of the system are measurable. That means the matrix Y is equal to the matrix X. In general, that doesn't happen in most systems. So Y is basically a subset or some combination of values of X, which really becomes measurable. So here what we are really assuming is control theoretically known as full state feedback. So as we have discussed earlier, that it is basically this positioning of the poles that are going to control the transient response and the frequency response, damping ratio, and everything about the system, like we also saw, right? The settling time, rise time, everything is controlled by this position of the poles, right? So what we are going to do here is figure out the method of this pole placement, so that if we choose a suitable control design matrix or gain matrix for the system in its state feedback, then the position of the poles is as we desire them to be. So what really we are doing, we have an open loop system. We want to close the loop with a suitable gain matrix for the state feedback. The motivation is we have a certain idea that for the entire closed loop system, the response of the system should be following some damping requirement, following some frequency response requirement, following some transient response requirement in terms of settling time, the damping ratio, and all that, right? So based on these requirements, we will fix the position of the poles, and based on this fixed position, the desired location of the final poles of the closed loop system, we will accordingly design the gain matrix or the feedback gain of the system. Okay, so it's like a reverse kind of thing. Okay, so we are considering this kind of a setup. So you have this X, which is the state variable, right? Now the differential of X depends on two things, AX plus the control input U multiplied by this B. Okay, so that's your system right now, and output Y, which right now for us is Y equal to X. In general, Y is equal to, goes through a transformation matrix C, so Y equal to CX, right? So this is the equations we are assuming for the plant in its open loop here, right? So you have this external input U coming up, and as you can see right now, this U is still not linked up with this Y or X in some way. So we are just assuming that there is an open loop input. This input U is not generated by looking at the value of X or something. It is just some input, and it is transformed by B, and you add with that the AX, and that dictates what is going to be your differential. That is the evolution of the plant, right? So that's how we are modeling this open loop system, right? Now, first of all, as we said, we are going to make this assumption that Y is X. That means it's a full state feedback. Now, what we are really going to do is that if each of this third point itself, if each of these state variables is fed back to the control U, then we are assuming that this full state X of the system goes through a set of gains Ki's of size n, let's say a vector K of size n, so that this X get itself transformed through this n-sized vector K, and then it is going to generate the U, right? So here in this picture, you have this U, and we are not characterizing U, but now we are saying that, well, U is nothing but it's basically a signal generated by looking at what is the X or the Y. In this case, X is equal to Y, Otherwise, it would have been y, right? And then from this x, you multiply it by a feedback gain matrix k and get your u. Now the question is how do I choose k? And that is basically the whole question of state space state feedback based linear control design. Okay, so this is what happens now, right? So what we want is we want to design this matrix k. Is everybody with me till now? Whatever have I said, I mean, is that understood?
Yes, sir.
Okay, so what we are saying is this: we'll put this block here, right, of our feedback vector k in such a way that it's basically transformed in this x, and that is generating the u, right? In a general figure, what we'll have is we'll have a reference signal like this here, right? But for our simplistic purpose, we'll now equate this r to 0. So with this, we can, for each of these summation points, we can write the following equations, right? So we can write this x dot is nothing but ax, as is coming from the block diagram, right? Ax plus bu, where u is nothing but r minus kx, right? And in that way, this is your the equation of x dot, right? Y is equal to cx, and we will assume this y equal to x itself, right? So right now, as I said, based on our assumptions, we are going to put this reference to 0, because fundamentally in my design, this is not going to change anything. We will see later on how to bring this reference back and all that, right? So with that, then what is going to happen is this minus k block will write directly to the u, right? So this is what we are going to get. So you have minus k and then u, right? And then it's multiplied by b, and this is how this is going to look like, right? So then my equations become as simple as that. So as you can see, we have set this r equal to 0. So we have nothing but x dot equal to a minus bkx, where this u is nothing but minus kx, right? So this is basically my overall closed loop dynamics of the system, that the differential of x is a minus bk into x, right? So this is the final closed loop system matrix then, because the derivative of the state is linked up by this matrix with the current state, right? So the eigenvalue of these matrices are going to be are going to be the pole positions, right? So and the positions are going to control what is the stability criteria, what is the transient response characteristics, and all these things about the system, right? So what we really want is, right now, this value of k is unknown to me, right? So what is the problem here? The problem is I want to design these values of k in such a way that the entire matrix A minus bk, its eigenvalues, which are the final poles of this closed loop system, get located where I want them to be, based on my desire of the system's response characteristics. Am I clear?
Yes, sir.
So I have something in mind that the system should behave like this. This should be the damping, this should be the settling time, this should be the rise time, blah, blah, blah. Based on those ideas, I am going to put the poles at certain locations. Now, as we are saying that those locations are nothing but this A minus BK's eigenvalues, right? Now, the question is, what should be the values of this unknown K, so that the eigenvalues of this matrix becomes as we want them to be, right? So that's it. This is the very simple technique of pole placement based control design, and this can be done using various possible ways, like this direct substitution method, Ackermann's formula, and also there is something called this transformation matrix P. So we'll see how they work. So very simple actually. So first we are given the system. So once you are given the system, you know what is the A and B matrix, right? So what you do is you take this overall matrix called the state controllability matrix. So that is a collection of B, AB, A square B up to A n minus 1B, right? Where n is the number of state variables in your system, right? Now, why do we take this special matrix? This is called state controllability, because if the rank of this is same as n, then actually, I mean, there is a proof which we are skipping here. Then it can be shown that control design for this system is anyway possible. That means it is possible to place the poles arbitrarily anywhere in the system and still get a desired value of k. That means the solutions are going to exist. So that controllability check can be done by using this matrix. Once that check is done, then we go for doing the real thing, right? So what we do, our overall problem is to design this k, right? So there are going to be n components in k, and I want to find out what are those, right? So then that's my feedback gain. That is the controller, right? So as we have said, it's nothing but one. So this was my equation, right? I mean, this x dot equal to a minus bk. That means, if you remember, while computing the eigenvalues of the characteristic, first you deserve the characteristic equation, right? So it would be nothing but, if I take this in S domain, is going to be Si minus a plus bk. So that's going to be the equation, right? So you take that as Si minus a plus bk in the S domain, and the determinant of this has to be the desired characteristic equation of the system, right? Now, how do I get that? As I have said, we are always going to put the poles as we please them, right? So let's say we decide that for there are n number of poles, because it's a nth order system, and they are going to be located at the locations mu1, mu2, like this up to mu(n), right? So then, since these are the exact location of the poles, the left hand side tells me what is going to be the characteristic equation of the system. Now, based on these values of k1, k2, k3 unknown symbols, we also know that, well, then Si minus a plus bk equal to 0 is my system. I mean, and if I take the determinant of this Si minus a plus bk, that's also going to give me the characteristic equation, right? So in that way, you can equate both sides, right? So what you do is, well, first you write the desired pole locations. So you get this left hand side, and you solve this left hand side, right? So what you are going to get is an nth degree polynomial, and for this nth degree polynomial, you are going to have these coefficients alpha 1, alpha 2 up to alpha n, right? And then in that way, you just get similarly from this determinant of Si minus a plus bk, you are going to get another polynomial of the same order with the same number of terms, and by equating alpha 1 with the corresponding coefficient of s to the power n minus 1 in that equation, you get the value of alpha 1, similarly alpha 2, similarly alpha 3, like that. So let's see through an example. So suppose this is my system given to me in the ax plus bu form, right? So a and b are given. We are interested in figuring out what is k, right? So fine. This is a third order system. As you can see, there are going to be 3 poles, right? So let's decide that the poles are located at these eigenvalues, right? I mean, so these are the desired eigenvalues, or these are the desired pole locations. So let there be one real pole and 2 complex conjugate poles, right? -2 plus j4, -2 minus j4, and one real pole on the left hand plane -1, right? So let's there be the decision now, right? Now based on this, we can easily design the state feedback matrix, right? How? Well, first we'll do the controllability check like we discussed. So we'll just figure out, well, what is CT, B, AB, and A square B. So it comes out like this, and we just compute its rank. It's same as 3, which is the dimension of the system. So we are saying that, well, in this case, the system is then completely state controllable, and it is possible to place poles arbitrarily. Since it is controllable, I can place poles wherever I want, because even in all cases, I should have a solution of the K matrix. Okay. Now let this K be this K1, K2, K3, right? So take this Si minus A plus Bk in this form, where I already know what is A and B, right? And take the determinant. So as you can see, you have this Si, there's the identity matrix multiplied by S, right? Minus A, the A matrix of the system, plus B, the B matrix of the system, and K, which is the unknown matrix to be synthesized, right? So for this, if you take the determinant, this is what you get. So as we said, this is going to result in a third order polynomial, right? And it has. And you have coefficients of all these terms, right? So these are going to be my alpha 1, alpha 2, alpha 3, like I discussed previously, right? So coefficient of a square is something, coefficient of s is something like that, and right. Now we have also thought what would be our desired pole positions of the eigenvalues, and accordingly I can write that polynomial and again find out what are the coefficients of these different terms in the polynomial, right? Fine. Once this is done, you can just equate them term wise and you get a system of n equations with n unknowns, solve them, and you get the values of k1, k2, and k3, and that tells you what is the final matrix K. So it's as easy as that, right? So this is your method of this designing the feedback in K using this direct substitution method. Any questions on this? Hello?
No, sir.
Okay. Fine. Then let's move ahead. There is also another method. We will soon understand that the other method is nothing but, so this is like a step-by-step method we have discussed, right? So you construct this determinant, you construct this characteristic formula and find this, you just match these terms, their coefficients. That's going to give you a set of equations and then you solve the equations. Now, Ackermann's formula is a technique in which you just need to, you don't just need to remember it, it's like a formalization of the entire thing. We'll see how it works. So the controllability thing remains same. You have this matrix, right? And you just check whether it's controllable or not, right? Now we come to point 2. All we are going to do is we have a straightforward formula which is just telling me what is the value of K, right? Now how the formula works, so as you can see, there is a K is given as this K equal to first this kind of a null matrix, and then you have this B, AB up to AN minus 1B. So basically the controllability matrix, and then it's inverse actually, and then you have phi A. Now what is phi A? Phi A is nothing but it's a matrix polynomial, I would say. So it's basically a polynomial defined on the state matrix A, and its coefficients do have some special characteristics. So let's see what is that. So again the similar thing, you have the system, and suppose you have a set of desired pole positions, right? So what you do is, well, you first do the controllability check, right? And it says that it's 3, rank is 3, so it's all completely controllable and all that. Now we are going to apply the Ackermann's formula, but as we saw, the issue is, well, I have this K is first a null all 0 followed by 1 matrix, then I have the controllability matrix inverse, and then I have a matrix polynomial with some coefficients. These coefficients are nothing but they are the coefficients of the desired characteristic polynomial. And the desired characteristic polynomial is something which we already know once we have fixed the position of poles, the desired position of poles, right? So given this desired position of poles at 2 plus 4j, minus 2 plus 4j, minus 2 minus 4j, and minus 10, you can write this characteristic polynomial, and from this you get the values of the coefficients alpha 1, alpha 2, and alpha 3, right? So this gives you the coefficients here, and then you can easily write the matrix polynomial phi A, right? So what is phi A? Phi A is because we have the coefficients as what 14 to this 14 and then 60 and 200 like that, right? So I have this, right? A cube plus 14a square plus 60a plus 200i, right? And we already know what is A. A raised to the power 3 plus 14 a raised to the power 2 plus 60 a raised to the power 1, like that, right? So this is my matrix polynomial phi A, which looks like this, right? Now all we do is just write the Ackermann's formula and solve it out, right? So you just write it like this. You have the 0, 0, 1 matrix. Then you have the inverse of the controllability matrix, and you have this matrix polynomial phi A. Solve this, you get K directly. So all these are implemented as standard routines in MATLAB, using which you can just compute them. So we have some examples on this which you can see here. Any questions?
Oh, sir.
Okay. So there are a few variations to this. So just to discuss that. Yeah. So if you remember, we have been speaking of the reference and all that. So with the reference, the system is not going to change, but there is something more I would like to talk about here. So in typical control theory books, you will see that this idea of this block diagram based view is a bit different in different places. For example, this is another view which is quite possibly used and in many practical systems is relevant, where you have a feed forward gain f. Okay. So this reference signal R will be amplified by this feed forward gain f, and then you have this plant. So as you can see, this is your plant, right, which is the x plus bu part. And then the question becomes, well, you are not only going to design K, but you have to design a K and a F. So this dotted part is the open loop, and you are trying to close the loop with this design of K and the F. So is this clear?
Yes, sir.
Okay. So if I have to do that, as you can see, if you just write out the equations at these junction points. So earlier we had this x dot equal to ax plus bkx like that. Now there will be this term bfr, right? And my control signal u, which earlier was this kx plus r or just kx, is now kx plus fr, right? Now for this, my overall control law is kx plus fr, and the question is we have to design k as well as f, right? Well, everything about this will remain the same. So just to tell you that in this case, while our design of K would be same as we have been discussing earlier, the design of F would be like this. So there would also exist a formula like this for getting this design of A. So this thing also you can see, but for our purpose, we'll just follow that original thing. So we'll just consider that, well, the R is actually 0 and we don't have a feed forward gain. That's the standard we'll be following. Okay, but this is just for your knowledge that, well, there are in many systems where you need that F as a necessity of the design, and you have to solve for that also, right? And for that you have to have this value of F and things like that. So of course here the overall system, as you can see in the closed loop, is again y by r, and in the equation the F will start showing up, which was not showing up for us, right? For us earlier it was just C Si minus A minus Bk inverse like that, right? But here it is showing up. And by the way, when you are going through this slide, notice one difference with the original ones that I used. We have been using a minus k or something, right? But here it is k, and that is why instead of a minus bk, which was the notation in our original, and that's the notation we'll be following, here it is a bit different, a plus bk. So I don't want to mix things up. We'll follow that original slide, but here this one I'm just showing to tell you about this f part. Okay. So overall, if somebody says, well, what is the process that we are going to follow, then from the time domain, we have certain requirements of settling time, rise time, and from the frequency domain, you have certain requirements of gain merging and phase merging. We are skipping this part right now. We are going just with requirements from the time domain, and from that, somebody tells you the location of the desired poles. We are thinking that, well, this is something designed by a pure control engineer, right? So he is going to tell me all these things. What are the desired poles and all that? And based on that, we are going to apply the methods we discussed, and we'll get the location, the state feedback gain, and all this stuff, right? Now, well, what happens when we switch this entire design thing from the analog to the digital domain, right? Well, a lot of things change actually with respect to this theory. So, what is going to happen now? If you may remember, that we have to sample the continuous system's output, which is a continuous time output xt, and the sampler is going to give me sample values of this continuous output at the logical times tks, right? So kth instance, k plus 1th instance, like that, right? But these values are analog values, but sampled at discrete time, right? Now these values which are analog but sampled at discrete time, they get converted to digital values using this A2D interface. So now your control algorithm is going to work with these digital values, and it's going to provide digital control outputs, which will be again converted to analog outputs, and that is going to be your UTK, right? So these are analog outputs, but they are provided at sampling times tk plus 1 like that, right? So they will now go through a whole circuit to generate a continuous time output UT, and that's what goes as a feedback to your continuous time system, right? So that's how it's going to work in the digital domain. So like I was explaining, your X, which was like this, is actually getting sampled at certain points of time at tk plus 1 like that. And similarly, your U, it's basically a continuous signal, but it's getting updated only at these values tk plus 1, and inside any interval between tk and tk plus 1, that U value is always constant, right? So let's think that, well, how this is going to work. I mean, how I am going to transform the dynamics of the system from the continuous to the discrete case. That's an important thing, right? And so if you remember, my original equation was this x dot equal to x form, right? If I just write it in this matrix form, it's like this, right? So I mean, just think of the x in terms of this phi. So derivative of phi is fi, right? In that form, we have the closed loop system, right? Now, the question is, we have to discretize this. Now, what we do is, well, we are all aware of this E series of phi, right? First of all, if you remember, well, if I am going to integrate this equation, what I get is some e to the power at term is going to come, right? So from this differential equation, I can write in the continuous time the value phi t is nothing but e to the power at, with the initial value of phi being identical, right? This is the identity. Now at, I mean, we can always have a polynomial expression of the this at term like this, right? So how do you really transform from this continuous time domain of the system to the discrete time domain? So the first thing that you can do is take a Laplace transform like this, right? So from this equation, I can write this equation, and then I can take an inverse Laplace transform, right? Why I will take that inverse Laplace transform, we will explain later on. Okay. Of course, I mean, so in that way, we can write it like this. Are you able to map how this x dot t, this equation, comes to this Laplace transform equation?
Yes, sir.
Anybody who is having an issue? Okay. Fine. So when we do this inverse, I hope from this to the next line is clear. So what's happening, as you can see, I can take L inverse, right? So that is actually going to give me this SI minus A whole inverse thing, right? Because what I'm really doing is, I will take this term on the left hand side, and then I will take the L inverse thing, right? So that would really give me this equation, right? So in that way, starting from the differential equation, we are trying to do what? We are trying to arrive at a continuous time equation where, suppose somebody has given me x0, I can compute xt, and it comes up to be like this. Okay. Now, why are we really doing this? We are trying to figure out, suppose somebody gives me the value at xtk, what is the value at xtk plus 1, right? So we start with this original continuous time equation, and we can arrive at this kind of an equation which is telling me, well, given x0, what is xt, right? So that's what this equation is telling me. And I hope this part is clear, right? This is what happens when you take the inverse Laplace transform of two terms multiplied like this, right? So you have SI minus A inverse PU its entire Laplace transform, right? I will have a more elaborate thing provided to you. Now coming here, suppose this equation is there, right? Suppose we have this equation. Now let's set xt as x0 as xt. The initial condition, let's set this at tk, right? So we have xtk here, right? And h is the sampling period, that is tk plus 1 minus tk, right? So if I say that I know what is the value at tk, right? Then from this equation I can simply write it like this, right? So the time interval t is now tk plus 1 minus tk, which is h, right? So I have x at tk plus 1 equal to e to the power a, this time difference with the initial condition this, and I integrate over this time difference, right? That's was because I was integrating from 0 to t, so I will now integrate just from 0 to h, and I have these terms, right? So if I take this equation, now I can write it in a form, as you can see, where I have x tk plus 1 in an expression built with xtk and utk, right? I mean, of course, with two more matrices, and these are nothing but the first matrix phi is e to the power ah, and the second matrix capital gamma is nothing but this 0 to h as b ds, right? So what is the importance of this equation is that it is nothing but the discrete time variant of the original continuous time equation. Am I clear?
Yes, sir.
Now, when I have this discrete time variant of this original continuous time equation, all my ideas of control law design and everything, I can just keep on working on them in a similar way, right? Because everything remains same, right? Only thing is that I am just working instead of the continuous domain, but I am working in this discrete domain, right? Because we know that when you are in the discrete domain, what is going to change? In terms of stability, earlier when I was in the continuous domain, in the Laplace domain, we are checking for poles located, I mean, whether they are all in the left half plane or not. But now the condition is basically in the Z domain, right? And the condition becomes whether the poles are all located inside the unit circle. So now in the Z domain, the location of the poles and the conditions for stability just change like this. So you have this unit circle. If the poles are located inside this unit circle, it's stable. It's on the unit circle, it's marginally stable, and outside the unit circle, then it's unstable. Now we understand well what are going to be my working steps. So if I am given a system like this, continuous time system, let's understand that there is a dependency of the final system stability on the sampling period. Can anybody tell me why? Hello? Hello?
No, sir.
So you see, this is our original system equation. And this is we have already discussed, given this equation, how we can form the discrete equations. Is that understood? Hello?
Yes, sir. Yes, sir.
Everybody? Anybody who has any issue, please tell me. How to get from the original equation up to this, is that understood? Hello?
Yes, sir.
So fine. So you start with these continuous equations, and now you can derive these discrete equations. But how do you derive these discrete equations? Basically, we have seen that phi is nothing but e to the power ah, and this capital gamma is nothing but integration 0 to the power 0 to h e to the power as bds. Is this fine?
So there was one problem. So when did this S come from? So initially it was T minus tau.
Yeah. No, the S was always there, right?
So could you go back one more slide?
Yeah. Oh, this one you are
So
saying.
yes, sir.
Mm. Yeah, so this T minus tau will make a change of variables here. That's a step jump here actually. So this is a fixed interval, right? That becomes H, right? Now, I mean, this S has nothing to do with Laplacian S or anything. Okay.
Okay. Yes, sir. So
So
it is
here
just
you
the
had a
variable
T
inside.
minus tau, and here you have a tau, and you have d tau, right? So all that we want to do is just, I mean, just keep it like this. I mean, this is another variable. So basically, e to the power a something, b of some p. I mean, u. See, u is also fixed, right? Because we are saying that we will start this thing from at some point that is tk, right? So there are a few things to observe in this equation. Thanks for stopping me here. So in this original equation, we are looking at starting from t equal to 0 to t equal to t. We are looking at a t time window, right? Now, what we do here is we take a constant time window of size h starting at tk. Am I clear? Hello?
Yes, sir. Yes, sir.
So we put x equal to tk, I mean x tk, and this becomes h quite naturally, right? Now the other thing is here again, my integration interval was from 0 to t, right? But what is the variable in this term? Is that variable t? No, the different, you can see it is d tau, right? So it's something else, right? So now what we are doing is we are making this interval 0 to h, right? So you can just think like this is a constant h, because in this, I mean, my point is in this integration, you see the this t is not a variable. This t is just an upper bound, the limit of the integral, right? So which for our case will become h. So we are instead of writing t, we are writing h, 0 to h. So it's just a replacement of t with h, right? What is the variable of this integral? The variable actually is tau, right? So all that we are doing is we are writing that in terms of s. It could have been anything. It could have been tau or anything, right? But what we do is we bring out the constant term, right? So we are saying there is one very important thing to observe here. See, in this equation, as we said, inside this interval 0 to 2, you have certain terms which are all dependent on tau, right? Which are the terms dependent on tau here, and which are the terms independent of tau here? Anybody?
So e power at is independent of tau.
E to the power a t minus tau has tau. B is free. U tau is also a function of tau, and d tau, that is the derivative variable, right? But observe one thing. So B is actually outside the integral. Now observe one very important thing from the zero order hold. When we are doing a zero order hold, my value of u doesn't change over the interval. Am I correct?
Yes, sir.
Because of what? It is always being updated at the sampling period end, right? It is always being, because it is calculated here, then the analog value, I mean, it is converted. I mean, this thing will fire only at the sampling period end, and then instantaneously this value will go up, right? So inside any sampling interval, this u tau is constant, right? So although in the analog variant u tau is there, what is going to happen in the digital variant? When I am having an initial condition utk, it will remain equal to utk inside the entire interval starting from tk up to the point tk plus 1. Am I correct?
Yes, sir.
Yes, sir.
So
So, but
UTK,
there
yes.
is one. So then, I understand that we are doing it for an interval of h, but the lower limit shouldn't it be tk and the upper limit should be tk plus 1, because that would be different. Uh, sir,
Yeah, I
sir,
am
if
coming
you
to that. I am
could
coming.
understand what.
I am coming to that. Please
Yes,
wait.
sir.
Please wait. So in this equation, you put the. I mean, what you do is, I mean, this is from 0 to t, right? Now let's say you. I mean, you write that as you said. You write it as tk and you write it as tk plus 1. Fine. And you have here utk. No problem with that. And it will become constant and it will go out, right?
Yes, sir. Yes, sir.
Now you do a substitution of the variable. Take the variable and subtract with subtract tk. So that would give you the lower limit as 0 and the upper limit as h, and this will and this will become this some the very I mean this ua tau, something like that.
Okay, sir. Okay,
Got
sir.
my point?
Yes, sir. Yes, sir.
Because you see this is uat, right? So when you do this 0 to, I mean, if I am going to replace them, so I am starting from tk. So this is tk plus 1 e to the power a. Here in the argument, I will have what? Tk plus 1 minus tau b u tau d tau, right? And u tau, I mean, this becomes tk, right? And this will go out, right? So I have u a tk plus 1 minus tau b t tau, right? Now again do that variable change as I said. So what it will do, it will put this one as 0 and the upper one as tk plus 1 minus tk, and this will just have this I mean uat, that one, because of that variable change, the other part will vanish. This is actually worked out in detail in one of my notes, and we will upload that. Okay, it is not that much detailed here in the slide. It's a, I mean, it's just a change of base. That's all. Okay.
Yes, sir.
So what do we see is finally from this we can write this thing, right? But as you see that the value of these matrices phi and gamma, they depend on h. Am I correct?
Yes, sir.
Yes, sir.
So they not only depend on the closed loop, I mean the on the continuous time matrices A and B of the state space matrices A and B, the discrete time. So this phi and gamma are what we call as the discrete time state space matrices, and they depend on H, right? So as you can see that if I change the sampling period from H to some H prime, the matrices are going to change. Am I correct? So where I am going to shift from a continuous time control to a discrete time control, what is my choice of sampling period has got a huge role to play with the performance, stability, and everything of the system. So, and the rest of the things remain same. So what you do is you just do this transformation with a suitable choice of H. This transformation is going to give you this phi and gamma. Once you get this phi and gamma, you check the controllability, you apply Ackermann's formula and all that. And I mean, of course, you have to choose your values of this k. I mean, these poles such that, I mean, they are located at your favorite points, and then you apply this method to get the controller gains and all that, right? So, like we have been discussing, so you place the system poles at certain positions, and you design this k and f by suitable application of this Ackermann's formula. So so this is your system of equations in the discrete domain, and then from the discrete domain equations you are saying that, well, I will choose the poles such that they are located at alpha 1 alpha 2 like that. So then you write the characteristic equation of the system with this choice of poles at alpha 1 alpha 2 alpha 3 like that, and then you determine that matrix polynomial equation like we discussed. and then you get this h phi, or that phi a, it was in that earlier other slide, right? And then from direct application of the Ackermann's formula, you can work out what is going to be the position of the poles, position of the, what is going to be the values of the gain components of k and f and all that, right? So whether it's in continuous time or whether it's in zero order hold based periodically sampled system, the overall thing is same. Only difference is, well, if it's a zero order hold based periodically sampled system, you have to compute these matrices phi and gamma from your original matrices A and B with suitable choice of sampling period H, right? And the rest of the things remain almost same. So that's your summary of how we'll be designing the controllers in both discrete time and continuous time. Well, in our tutorials, we will show how to do these things in MATLAB and all that. And the next thing, now you can understand that there is a huge impact of what is the sampling period chosen for implementing a controller. Can you just think of how this will have a role to play with scheduling?
So the H will depend on how fast we can take a sample and compute a U. So that would require scheduling.
Yes, so what is going to happen is, see, you have this controller U equal to minus kx, right? Your plant is going to evolve as per this equation, xk plus 1 equal to phi xk plus gamma uk, or if it's in the continuous domain, x dot equal to x plus bu. So this is in the hand of the environment. But what is in hand of the computer? In hand of the computer, this is what you have to do, right? You have to implement a C program or something which is going to execute this matrix multiplication of k and x, considering that you have implemented a controller following this method. If you have implemented a controller in some other method, there will be some other matrix inequality equation or something else, right? But anyway, so this multiplication of k by x and all that is like a program, and this program has to run with that same period of h, right? So that's like a task running with the periodicity of h. Now consider that you have a shared processor, many controllers, all of them are running with some periodicity, and they have been co-scheduled using EDA for RMA or something, right? So that's the link between the performance of the control loops and the scheduling, sampling period, schedulability, and everything that we have discussed earlier. So that's where you have scheduling interacting with control design, and that's the true objective of CPS design that is coming into play. Okay, so well, we'll pick up with things from this point in the next lecture. Thank you. So please study well for the test. Any other question? I think. Oh, I think this we have already answered. Yeah. Okay. Any other question? Anybody? Hello. Hello.
Sir?
Yep.
Sir, for the exam, sir, where do we submit our answers? I mean,
Okay, so we are going to announce, we have created a submission page for this course in Moodle. So we are going to put an announcement in the announcement channel in Teams, where we will give you that course details. So by the way, all of you can, Ipshita, we have to include all of them in Moodle, right? Or they have to create a login. What is the complexity there? Hello.
It is like they have to create an account, and we have given them the code in the announcement channel. They have to join with that code.
Right. So either you have a so by the way, this is not Institute Moodle. This is Computer Science Department's internal Moodle server. Okay. So there we will be creating this thing where you should be getting the you see in the announcement channel that Moodle's page link and everything is there. So you have to register yourself there. During the exam, the question will be there. and there itself we have to upload your answer script and all that. It will be a pen and paper exam, like you just follow my announcement that I posted last week, pen and paper exam with all details. So that's how you have to upload there. Okay.